Hi, my name is Bernard Brault, and I want to talk to you about quantum mechanics with respect to light, light being photons, radio waves, and how they can interfere, how it can be, lenses and mirrors and different things like that. But from a quantum mechanic approach. And so, because it's going to be quantum mechanics, just please bear with me. It's going to be a little bit of math background, for those of you maybe in physics or those that might remember some of the stuff that we learned about quantum mechanics. So I'll give you a little bit of an overview, and then it's going to get much simpler, and eventually it's going to be pretty intuitive, and you'll see that it's going to be a lot simpler than anything you've seen before, looking into the traditional waves, if you want, or the way you might have learned it maybe in college using like electromagnetic wave and traditional waves. So in quantum mechanics, what you have is you have a wave function. Nature likes waves, and the reason why nature likes waves is because nature likes everything that sort of like oscillates. And wave, they oscillate both in space and they oscillate in time. If you look at waves in the ocean, right, you can take a snapshot and you can see basically the water going up and down, and it might go up and down not just like periodically, but it might have some crest, and some of them overlap, and some complex waves and so on. And you could also look at it in one particular position. You could put a floater someplace and look at the buoy go up and down, and so it does go up and down in space. It goes up and down also in terms of like time, and it propagates, right? So it moves out just like a real wave. So a wave is a function of position in time. So this is the wave function right there, position in time. And the first equation there is called the Hamiltonian. And the Hamiltonian has to do is an operator. It transforms the wave function into another function, and that other function happens to be the energy operator. And we call it the energy operator because what you have is you end up getting eigenfunctions that, with energy coming out of it, so as a scalar. And so the simplest wave equation that you can actually do in mathematics is this equation 1.1 here. It's E exponent ikx minus wt, w being the angular frequency, and k being the spatial frequency. That's a spatial frequency right there in space, right? And this is the most boring wave. It's almost like a tone. You listen to music and you hear these complex, tones that are like notes that have like multiple frequencies, and they're very rich, versus you hear a simple 440 hertz tone and they just go beam. It's very, very boring. So this is the boring wave, the most simplest wave that you can imagine, right? But it's the reason why I picked the simplest one is because it's the easiest one to solve mathematically as well. It turns out we learned that for photons, the frequency relates to the energy, right? So the energy of a photon relates to the frequency of the light, and the momentum relates to the wave number, or the spatial frequency, which is p right there. And if you apply the Hamiltonian specifically to this one, and here's the equation number 2, and you take the time derivative, and that's a very easy derivative to take, right? Because derivative of an exponential is just whatever is on top there times the exponential itself. So what you end up with is that the Hamiltonian for this particular wave function, the simplest wave function, what it gives you the energy times the function itself. And because it's the energy times the function itself, because it returns the same function times a scalar, this function there is called an eigenfunction, and this is the eigenvalue. Actually, it was designed this way. The people didn't come up with this operator out of the blues. They came out of the operator. It was reversed engineered to get exactly this result. Now, you could further divide this into two components. You could separate the frequency, the time-dependent component from the spatial component. So the x can be extracted out, and then you end up with the energy time, the time frozen space, if you want, wave time, something here that's called a phasor. And the last section right there is something that's of always magnitude 1, but has different angles. And that's what I'm showing right there. You see that little blue arrow right there? So at time t equals 0, this value is equal to 1. And as it evolves in time, it rotates around here like this. And this is a phasor. It's actually a complex number, right? So don't be afraid. It's okay. It's just an arrow in time and always has magnitude 1, but then it rotates around, 360 degrees, and then keeps rotating. So that's basically the phasor. It's good. So this is the worst part about the math. It's going to get easier, right? So I'm going to just focus on these little arrows now. So the phasor here is something that spins around, and for visible light, it spins around like extremely fast, right? So it's unbelievable how fast it goes. Actually, this will spin around 430 terahertz. That means it's 430 times 10 to the 12 spins. It's going to spin around like crazy. So light goes really, really fast, speed of light, right? And really, how far does light have to travel, or radio waves have to travel, before this phasor spins around like a complete circle and back to itself? Depends on the frequency. So for visible light, 1 micrometer, that's how long it takes, or in order for that arrow to spin around completely over itself. And 1 micrometer just happens to be more or less like the smallest thing you can see using a microscope, right? So over 1 meter distance, visible light will spin about 1,000,000 times. Actually, blue light will spin even more, maybe 2,000,000 times, and red light is going to spin only 1,000,000 times. For electromagnetic waves, it's going to take much longer distance. So what you see here is for Wi-Fi, mobile phone, things that operate around the gigahertz or 2 gig, 3 gig frequency, it's about 10 centimeters. So that's about a foot. So by the time a photon moves a foot, that phasor will have spun around 180 degrees. FM radio, 100 megahertz, right? In your car, you used to listen to FM radio. Maybe you still do. It's a much smaller frequency, so it takes about 3 meters, right? So it's about a yard before it spins around it completely. AM radio, 300 meter, and then you could go down in frequency until you reach like ultra low frequency in the tens of hertz, and you'll find that light will take 40,000 kilometers all the way around the Earth before actually that phasor rotates 180 degrees around, right? So let's go back now and let's take a laser pointer, and let's shine a laser pointer onto the screen. And what we're sending when we're doing this, we're sending millions of photons, right? And then it just continuously, and you don't even see them, right? It just looks like a continuous light. You don't actually see the photons themselves. But if you were to send 1 photon at the time, right? So you take 1 photon, and that photon, if you remember through the Hamiltonian, right, it has a certain wave function, and then it evolves in time by being multiplied by that little arrow, which is always magnitude 1 but different angles. So as it moves to the right, remember what I said, it's going to spin around, and because it's going to have to go 2 meters before it hits the screen, that little arrow will spin around 2,000,000 times, right, for red photon. So it's going to the right, spinning like crazy, and keeps going to the right, keeps spinning, and there eventually it hits the screen, and that little arrow is going to have an angle, right? It's going to be somewhere between 0 and 360 degrees. And what's interesting is that if I were to move the screen to the right by 1 micrometer, right, 1 micrometer, this thing would have gone around 1 more rotation. So if I move the screen to the right by 0.5 micrometer, that arrow would actually be pointing 180 degrees. It would have gone around like half the distance. So just by moving this screen by, half a micron. Okay. So what can we do with this? Bear with me, you'll see it's going to get very, very useful. One of the experiments that you might have seen when you were like younger in college is the famous double slit experiment. And you can buy like what you see here is a picture of a slide, and if you magnify the slide here, you see it's got 2 slits. Actually, it has a 2 slit, 3 slit, 4, 5, and 40 slits, and it tells you the distance between the slits and tells you what the opening of each slit is. And then you can buy this and shine light through it, and what you'll see is interference pattern. Right, so you're going to see that developing on the screen. Let me try to make this smaller. Sorry about that. Just made it too big. All right, so let me put that back. So that film, you're going to put like about 1 meter away from the laser pointer right there. And several meters down, you're going to have your screen, and you're going to shine your light across this 2 little slits. They're very, very close to each other, maybe 0.1 millimeter, or very, very, very close. You get barely visible. And if you were to block one of the slit, what you'd expect to see is you'd expect the light to go through the upper slit and then hit the screen there and make a little blob right there. If on the other end you block the top and then you leave the bottom one open, what you're going to see is you're going to see the light going like this and make a blob right there. Where it becomes interesting is when you open both at the same time. Right, so when you open both at the same time, then you expect to see a blob of light up here, another blob of light, and they could be very close because these are very, very close together, so maybe somewhat overlapping, but you expect to see 2 blobs, and that's not what we see. What we see is this. We see like some kind of an interference pattern. So you see like a blob of red light, no light at all, completely dark, and then slightly dimmer light right there, and it just keeps repeating itself like that. And you see this interference pattern. Now, it's easy to explain this if you say, well, what we're shining across the film is a wave. Right? This could be like an ocean wave, and it hits like 2 different openings, and all of a sudden 2 waves come out from the top. A wave comes out from the top opening, and the second wave comes out from the bottom opening. And as they propagate, right, so the crest meets the bottom, and then sometimes they amplify each other, and sometimes they cancel each other. But here's the thing about light, is that sometimes we send only 1 photon. And when we send only 1 photon at the time, right? So the photon is going through either the upper slit or the bottom slit. And if you put a detector on the upper slit knowing that it went there, and you know they went through the upper slit, what you're going to see is a top blob, and there's be no interference. So, but when you're not measuring, and light has the possibility of going through both slits, it is sort of like the photon interferes with itself as if it had this light behavior. And this is the whole thing about quantum mechanics. So what we're going to do here in quantum mechanics is that we're going to look at the amplitude of those phasors when they hit the screen for all the different possible paths, because light looks at all the possibilities, and you need to add all the amplitudes from all the different possible paths to actually calculate the probability of whether or not it's going to hit the screen at a certain spot. And so if you look at this interference from the front, this is what you'd see. This is not red light, it's like more like a purple, but you see this dark and bright and dark. But when you send 1 photon at a time, that's not what you see. What you'll see is the photon's going to hit a certain spot. It might hit the spot right there, it might hit the spot right here, but it'll never hit where you see in dark right there. And so if you were to look at the probability of hitting the screen in a certain location, the probability function looks like something like this, right? So it has a certain amount of probability. It's going to hit right there in the middle, has a certain probability of hitting there, and basically 0 probability of hitting here, here, or there. Right, so that's what we mean by the probability of hitting someplace. So if you're going to send millions of them, you add them all up, and all of a sudden you see this visual pattern. But if you send 1 at a time, what you'll see is they're going to hit the screen in a very, very specific spot. You can never predict exactly where it's going to hit, but you can predict the probability of where it's going to hit. And I'm going to show you how to calculate these probabilities, and that's what we're going to do in the next couple of videos. And so bear with me, and we've gone through the worst. I think it's going to get more interesting. Let's see how many people are going to stick around for the next round. Thank you very much.